All right, we're doing Chapter 11 example problems, and I've got 5 problems here that we're going to go through. The first one is number 1 from Chapter 11 in your textbook. It says, what is the smallest positive integer n such that there are 2 non-isomorphic groups of order n? Name the 2 groups. So if we're looking for the smallest positive integer n, really we could say let's just start with n equals 1. And let's think about what different groups there are. Well, if n equals 1, meaning the order of our group is 1, the only group is the trivial group. Okay? Well, that's not anything exciting. There's only 1, so it can't be 2 non-isomorphic groups. So let's move to n equals 2. If n equals 2, our groups are going to be cyclic because n is prime. When n is prime, we know that our group is cyclic. So all groups are cyclic. We could call them E and A, where E is the identity. Our trivial group, by the way, we could say is just E. Well, n equals 3. N equals 3 again, that's prime. So all groups are going to be cyclic. So we'd have E, A, and A squared. Okay, well, what about n equals 4? Well, 4 is not prime, so it doesn't necessarily have to be cyclic, but it could be cyclic. If it was cyclic, we could have something like Z4. Let's see if we can think of another group that would be order 4 that would not necessarily be cyclic. Well, we could use our external direct products. We know that Z4 is not isomorphic to Z2 external direct product Z2. And we know that Z2 external direct product Z2 is order 4. So what's the smallest positive integer n such that there are 2 non-isomorphic groups of order n? It would be 4, and those 2 groups are Z4 and Z2 external direct product Z2. Show that there are 2 abelian groups of order 108 that have exactly 1 subgroup of order 3. Okay, so for working through this one, first let's think about what 108 equals, because that's our order of our group. 108 equals 2 squared times 3 cubed, if we did its prime factorization. So we know that we can write groups as external direct products if those 2 groups, like if we're using Z, for example, if our n's are relatively prime. Sorry, that didn't come out very clearly. So if we had like Z108, we could rewrite that as, like, say, Z4, external direct product, Z27. Now, we also know that we could rewrite this a little bit and have different groups that are also going to be order 108, but that they would not necessarily be isomorphic to Z108. So we know that these are isomorphic. We could also try to write it as, I'm just going to leave Z4 by itself. Z4 external direct product. Maybe we did Z3 external direct product Z9. This would be order 128, but it's not not 128, 108, excuse me. This is order 108, and it's not isomorphic to Z108. So this is just order 108. Another order 108 group that we could look at would be this group. Another 108 group that we could look at would be any of these three groups here, only splitting Z4 up into Z2 and Z2. Now, we want to think about what is going to be to our advantage here as we're trying to find a group that has exactly one subgroup of order 3. So we know we have these three groups. We also would have Z2 external direct product, Z2 external direct product, Z27, Z2, Z2, Z3, Z9, or Z2, Z2, Z3, Z3, and Z3. All of these are order 108. Now, if we're thinking about needing to have a subgroup of order 3, getting a subgroup of order 3 for any of these, if we had the identity element from either identity element from Z4s or identity element from the Z2s, then having an element of order 3 would just depend on what came from our Z27, Z3 external direct product Z9, or Z3 external direct product Z3, external direct product Z3. So, we need to be careful about our choice of these other ones here. So we are going to be carefully choosing between these. Which one of these would have exactly one subgroup of order 3? So we have Z27, Z3 external direct product Z9, or Z3 external direct product Z3 external direct product Z3. Okay. Now, we can go through and argue a few different ways. We could say, well, with Z3 external direct product Z3 external direct product Z3, we would have subgroup order 3 if we had 1, 0, 0, if we had the cyclic subgroup generated by that, or if we had cyclic subgroup generated here, or if we had this cyclic subgroup. And then there's more, we could have 2 of them be 1 and the others be 0. So we have a few options for what we could choose for having a subgroup of order 3. So we're seeing there that Z3 external direct product Z3 external direct product Z3 would have more than just one cyclic subgroup of order 3. So more than one subgroup of order 3. So we know that it's not this guy. So we're able to say it's not that one. Okay. We could use a similar argument on Z3 external direct product Z9. Well, how do we know that Z27 has only one subgroup of order 3? Well, for that, we're going to reference theorem 4.3, that corollary. And in that corollary, it says something along the lines that for Zn has only one subgroup of order D where D divides N. And it tells us exactly what that subgroup is as well, right? We would know that our subgroup would be Z27 has one subgroup, and it's specifically only one, if I can spell here, only one subgroup. Order 3, which is 27 divided by 3 would be 9. So this would be our subgroup that's order 3. And so we specifically need to have here one of our options where we had Z29, so we have Z27. Whew, I can't read today. So we have Z4 external direct product Z27, or our other option is Z2 external direct product Z2 external direct product Z27. And to think about what those subgroups would actually look like here, this one, the subgroup, would be, we would have 0, 9, and that would be a subgroup of order 3. And here our subgroup would be 0, 0, 9. So we've shown that there's exactly 2 abelian groups that are of order 108 that have exactly one subgroup of order 3. So we have just these 2 groups. All right. Suppose that G is an abelian group of order 120 and G has exactly 3 elements of order 2. Determine the isomorphism class of G. For this one, instead of writing it all out for you, I'm going to kind of just read through and explain the textbook's definition of the solution here. So elements of order 2 are determined by the factors of the direct product that have order of a power of 2. So we are looking for, again, let me pull it up on this other screen so I can write it down for us again. We have G, which is order 120. G has exactly 3 elements, order 2. We want to know the isomorphism class. So, we're really concerned about the elements of order 2 being factors in the direct product that have an order, a power of 2. So we really are just looking at here Z8, Z4 external direct product Z2, and then Z2 external direct product Z2 external direct product Z2. If we look back at theorem 4.4, Z8 has exactly 1 element of order 2. Z4 external direct product Z2 would have exactly 3 elements of order 2, and Z2 external direct product Z2 external direct product Z2 would have exactly 7 elements of order 2, which you could just use this theorem, theorem 4, and go through and find each of these. So the important thing is we're finding this one right here, that Z4 external direct product Z2 has exactly 3 elements of order 2. So this tells us that as we're thinking about breaking down 120, 120, by the way, is equal to what? Well, we could say that it's 2 cubed times 3 times 5, right? So if that's the case, then looking at this here, this would be what G would be equal to. Z4 external direct product Z2, external direct product Z3, external direct product Z5. The things that give us elements of order 2 is this part right here. That's what's giving us our 3 elements of order 2. And then we need the rest of this just so that we're able to get to our group being order 120. Number 26. Let G be this group under multiplication mod 96. Express G as an external and an internal direct product of cyclic groups. So first off, what's the order of our group? It's always a nice spot to start. The order of G is 8. That means that G would be isomorphic to Z8 or Z4 external direct product Z2, or it could be Z2 external direct product Z2 external direct product Z2. So let's kind of look at our elements and think about what order each element is. So you might want to play around a little bit, find the order of each element. You're going to find that there's no elements order 8. If there's no elements of order 8, that gets rid of Z8 as one of our options. Okay? Now we would look and say, okay, do we have anything that's order 4? Well, 7 happens to be an element order 4. So I clearly cannot write this morning. So 7 is an element of order 4. If we have an element of order 4, then we can't have Z2 external direct product Z2 external direct product Z2. We have that then G would be isomorphic to Z4 external direct product Z2. So we have an external direct product. Now we need to find an internal direct product. So we could use lemmas 2 through 4. They're at the end of the chapter. We know 7 is an element of maximal order. So we could say that G is isomorphic to the cyclic subgroup generated by 7. Internal direct product, let's find something order 2. Let's see. 17 is order 2, so I'm going to do external direct product with 17. And there gives me my internal direct product. I notice that I've used cyclic groups for each of these, so I am following the instruction of having cyclic groups that I'm taking external and internal direct products of. Now, for writing your internal direct products, you have a few other choices as long as you're using one that has order 4 and one that has order 2. You can replace 7 and 17 with other numbers from our group here. All right, 36. Suppose G is a finite abelian group. Prove G has order p to the n, where p is prime, if and only if the order of every element of G is a power of p. So, it's an if and only if, so we're going to have to do this 2 ways. Let's start with if the order of G is equal to p to the n. Well, then by theorem 11.1 and theorem 9.6, and look those up if you need to have a refresher, we see that all elements have to be a power of p. And that is clear and direct just from having those two theorems and the proofs behind them that we have in our text. So there's not much work to do for our forward direction. It's our backwards direction that we have to do a little bit of work on. So, if every element is a power of p, then let's use theorem 11.1 corollary. And we can look at external direct products of our group. And G can be written by taking an element of maximal order from each. So if every element is power of p, use theorem 11.1 corollary. We use external direct products, and G can be written by taking elements of maximal order from each part of the external direct product. To get element of order p to the n, thus the order G is p to the n. So kind of write that a little bit clearer so you can see it better. if G was isomorphic to H, external direct product K, external direct product J. What we're going to do is we're going to take elements of maximal order from each of these, and to find the order of that element, then we would find the least common multiple, which the least common multiple would be p to the n, which would then give us our order of our group is p to the n. So it's a careful use of theorem 11.1's corollary to say that we can look at those external direct products. And of course, we're also referencing theorem 9.6, our fundamental, that would be Lagrange's theorem, I believe, which tells us that our order of our elements have to divide the order of our group. So that is chapter 11, example problems. My brain's a little foggy this morning. I've been working on a lot of math, so I'm sorry if I stumbled through that a little bit. It's good for you to see my brain processing things. I hope that you guys are doing well, and if you have questions, of course, email me, and just stay in touch as we continue through this semester. Thanks for watching. Thanks for your time.